Okay, I want you to picture this. You're standing right there on the drill floor, and suddenly the drawworks has to drop 10 tons of heavy drill string. In that exact moment, your massive AC drilling motor is no longer consuming power, right? It's actually being backdriven. It is actively generating power, and that creates this massive, sudden surge of energy that has to safely vanish, literally vanish, as heat in an absolute instant. So you've got to ask yourself, where exactly does all that energy go? I mean, it has to go somewhere incredibly fast, because if it doesn't, well, you risk starting a fire or completely frying the electrical equipment room. Taking that massive pulse of electrical energy and safely dumping it as heat, that's the entire job of the braking resistor. Honestly, it's kind of the unsung hero of the electrical drive system, and getting the specs right on this thing is absolutely crucial for rig safety and overall performance. All right, let's look at the first major engineering choice you've got to make here, selecting the right tank. We're looking at atmospheric versus pressure tanks. When you're speccing out a braking resistor, you're essentially making three independent choices, starting with the tank that houses the elements. Now, atmospheric tanks, they just operate at ambient pressure. Super simple, very cost-effective, and perfectly fine if you just need moderate, intermittent braking duty. But what if you're expecting heavy, continuous braking, like sustained operations? You're going to need a pressure tank for sure. These bad boys are fully sealed. They're rated to handle elevated internal pressure, which means they can manage those intense braking events without violently venting a bunch of hot gas straight into your equipment room. So, if you're doing heavy tripping, the pressure tank is the way to go. Moving on to our next big choice, and honestly, this is the ultimate titanium upgrade. This next crucial choice actually has absolutely nothing to do with electrical performance. Actually, scratch that. It's 100% about survival, marine survival. We're talking about titanium encapsulation. By sealing the resistive element itself inside a protective titanium sheath, you're shielding it from that highly corrosive, salt-laden moisture you get offshore. It's not about boosting performance. It is a pure, straight-up lifespan upgrade to make sure your gear survives a decade or more out there on the water. Okay, let's get into the final specification choice. Cooling. Air versus water. So think about it. You've just absorbed this massive amount of electrical energy and successfully turned it into heat. Great. But now, how do you reject that heat? This follows the exact same logic we covered back in episode 4.1 with the VSD cabinets. Air-cooled resistor banks? Yeah. They're simpler and definitely cheaper, but they need clear airflow and they dump all that dissipated heat directly into your equipment room. Water-cooled designs, on the other hand, reject the heat through a closed fluid loop. And let me tell you, that is a real game changer if your resistor is sitting in a tight, already sweltering machinery space where you just literally cannot afford one more degree of ambient heat. All right, it's time to put all this together with a real-world scenario. Because here's the thing, you aren't just buying some off-the-shelf generic braking resistor. You are actively combining these three independent choices to fit your specific operational reality. So let's play this out. Imagine your rig forces you to shove the resistor into a really cramped, already warm machinery space. And on top of that, the rig is designed for heavy, sustained braking duty. Take a second and think about it. What exact combination of tank, material, and cooling would you specify here? Well, if you guessed this exact combo, you absolutely nailed it. First, you need a pressure tank to handle that sustained heavy duty without failing. Second, you absolutely must have a water-cooled design to ensure all that massive heat gets piped out of that cramped room through a closed loop instead of just baking all the surrounding equipment. And of course, because we're offshore, you've got to specify titanium encapsulated elements so the unit actually survives the harsh marine environment. See how that works? All three of those specifications perfectly answer a very different part of that exact heavy-duty marine scenario. And with that, we've officially wrapped up our hardware portfolio. I want you to zoom out for a second and just look at how far we've come in this explainer. What started out as these kind of abstract categories is now a highly concrete, real-world hardware portfolio. You know the exact difference between water-cooled ACS 600 and air-cooled ACS 800 multi-drives. You know that you need to check not just the kilowatt rating on drilling motors, but that crucial radial force tolerance too. You understand exactly why a Resiblock dry-type transformer's zero silicon build is a big deal offshore. And now you know exactly how to architect a braking resistor for heavy duty. You've got real, actionable vendor knowledge across the entire board. So you know the hardware. But listen, a pile of highly engineered hardware just sitting on a dock, that isn't a drilling rig. Next time, we're going to take all this equipment through the full EPCO lifecycle. That's engineering, procurement, construction, commissioning, and operations. But I'll leave you with this question to chew on. What actually happens when all this perfectly engineered hardware collides head-on with the chaotic, unpredictable reality of a physical rig build? We're going to find out in our next explainer.